Hello Priyanka, I am audible. I'm just checking my voice.
Yes, you are audible.
Okay, thank you. Okay, we will start and the rest we will, whenever the student come, they will join us. So we will start it. Hello everyone, welcome to the GATE NPTEL lecture course. Today we are going to learn the concept of Poynting vector in electromagnetic waves and then we solve some questions related to that. Um, I I'm just wanted to know, am I audible clearly?
Yes,
Okay. So let's start it with this concept of Poynting vector. There is two ways by which we can learn this concept of Poynting vector, and we are focusing on the way which are related to the electromagnetic wave. There is another way we can learn this concept is through conservation law, which is much more mathematical and will not be available. You will get in NPTEL lecture, but it is not that much useful from GATE perspective. So we will focus from the electromagnetic wave perspective. So you are familiar with this concept of electromagnetic wave that we have talked in last classes, that the electromagnetic waves are the vibrations of these electric and magnetic fields which are propagating perpendicular to each other, and they will also follow this wave equation. So the pointing vector will try to give an interpretations about how much energy that electromagnetic wave is carrying per unit time per unit area, and it is generally denoted by S vector. So similar to like electric and magnetic field, these electromagnetic wave carry forward the momentum and the energy with itself. And to determine what is the energy and momentum this electromagnetic wave carrying with itself, we use the pointing vector. So for the case of electric field, if we try to follow the wave equations, then the form will be like this. And similarly for magnetic field, the form will be like this. And where if you try to compare these two with the wave equation, the velocity of this Vm wave is given by 1 by square root of epsilon naught E naught, which is the speed of light. So basically, these are the simple formulations of electromagnetic waves, from which we can say that the electric and magnetic field follow Maxwell's equation, they will follow a wave equation and therefore kind of vibrating very much like an a wave. So these EM wave carry energy and momentum with it, and which is travel with this wave as well. So if you are familiar with this new technology in which lasers are used, so basically what it happen is whenever you have this electromagnetic wave is traveling and it carry energy and momentum, and you place another obstacle like surface and it hit the surface normal to this, so the energy and the momentum carried by this wave is then transferred to the surface. So depending on how much energy and momentum it will carry, there are different kind of applications that are evolved with time. For example, for the case of metal cutting, there is a very high energy is required in electromagnetic waves. So these are just an applications of this EM wave. And pointing vector is tried to interpret this energy per unit time per unit area. And similarly, there is this momentum density, which is the momentum per unit volume that is used to describe the momentum of this EM wave. So let's go to this mathematical formulation of this Poynting vector. So we will derive the formula for this Poynting vector based on this definition, which says that the Poynting vector S should be like energy per unit time per unit area passing through a surface. So basically, this is how Poynting vector is described. So if you have a electromagnetic wave and which hit a surface with area A. Now within time delta t, if its speed is c, it will cover a length c delta t. So basically, you have this length c delta t which is covered by this electromagnetic wave within time delta t. And this area is A. So the total volume is length into this area. So within time delta t, that much area is covered by electromagnetic wave. So if we are able to find how much energy is there within this volume, we can determine what is our Poynting vector. So basically, we wanted to know what is the energy within this volume. So the for the electric field, the energy per unit volume is given by this expression, 1 by 2 epsilon naught E square. The formula of it can be the derivation of it is available in this NPTEL lecture. Others we will continue from here. That the energy of per unit volume for electric field is given by 1 by 2 epsilon naught E square. Similarly, for the case of magnetic field, energy per unit volume is given by B square by 2 mu naught. So the total energy of electromagnetic wave is the energy of electric field and the energy of magnetic field, which is equals to 1 by 2 epsilon naught E square plus B square by mu naught. There is this formula that is valid for electromagnetic wave in free space. Uh, it is valid in free space that we can break the magnitude of magnetic field is related to magnitude of electric field by E by C. So B naught square can be written as E naught square by C square, and C is the velocity of this EM wave, and it is given by 1 by square root of epsilon naught mu naught. So when we put this value of C square, this is the expression that is coming for the B naught square can be written as mu naught times epsilon naught E naught square. When we put this into this formulation of total energy per unit volume of electromagnetic wave, this is comes out to be epsilon naught E naught square. So this is the total energy per unit volume. So if you wanted to calculate what is the energy in a volume V, so we have to multiply this energy per unit volume by this volume. So we are considering the volume which is covered within this distance delta t. So that volume is given by area multiplied by this length. So here the energy in volume V is given by energy per unit volume multiplied by the volume. So this is the energy expression. So we have to calculate what is the energy per unit time. So we will divide by time and per unit area. So we divide it by area. So this will give you the magnitude of this Poynting vector. When we divide this energy expression by time and the area will cancel out. Similarly, time will cancel out. So the magnitude of this Poynting vector is comes out to be C epsilon naught E square. And since energy density, which is energy per unit volume, is given by epsilon naught E square, so the magnitude of Poynting vector is related to energy density multiplied by C. Similarly, the direction of this Poynting vector is in the direction of propagating vector. See, if you have an EM wave which is traveling in this direction and it hits any surface, so basically it will transfer its energy here. So the direction of energy in which it is travel is the same as the direction in which the wave is traveling. So the direction of this Poynting vector is same as the propagation direction. So the Poynting vector is given by C epsilon naught E square in the k cap direction. And since the relation for electromagnetic wave B equals to E by C is valid, so using this relation, we can write B as epsilon naught mu naught E square. So Poynting vector can also be written in terms of magnetic field also. And since we can also modify this term further, like say B naught square can be written as P naught into B naught by mu naught. So we can write P naught as E naught by C here. So one C is cancelled, so we are left with E into B by mu naught. So the Poynting vector also written as E cross B by mu naught. This is the simplest way to derive the expression for the Poynting vector. Similarly, there is an expression for the momentum density of electromagnetic wave, which is given by Poynting vector by c square. This represents the momentum per unit volume. Momentum density means momentum per unit volume here. So, if you wanted to consider the intuitive way how this formula is coming, you are familiar with these equations of energy equals to mc square for the case of photon. So similarly, the momentum is given by energy by c. So and into c for the photon. So here, if you wanted to see momentum per unit volume, so here the energy per unit volume is given by that u, and from here, if you wanted to calculate u, it will be mod s vector by c. So momentum per unit volume will become energy per unit volume divided by C, and since U is given by mod S vector by C into C, so mod S vector by C square. This will become the momentum density, momentum per unit volume for the case of photon. The complete derivation of it is available on this NPTEL lecture. So now let's come to the intensity part. So whenever we talk about this electromagnetic wave, we are generally consider, you know, we consider it as a light. And in case of light means we are talking about a certain wavelength range, which is the visible range. So visible range is started from 400 nanometer to 600 or 700 nanometer. So this is the visible range, and in which if our electromagnetic wave is light, then we can say that it is our light. So whenever talk about the light, we are talking about this wavelength range. So mean wavelength is 0.5 micrometer. So if your wavelength is such a tiny wavelength, so within time delta t, there are a lot of oscillation that is happen within a small area. So if we want, for example, if you have a very thin object, within this thin object, there are lots of oscillations happen of this EM wave. So generally, we are consider the average value of this pointing vector or the average value of field to calculate what is this intensity is. And the intensity is generally average value of this pointing vector. So let us consider how we calculate these average values. So if for the you are already familiar that the electric and magnetic field can also be written in this form, the electromagnetic wave. There is also this exponential form e to the power I k vector dot r minus omega t in the escape direction. So basically, this is the real form of this expression. So both are equally valid. So if your electric is wave field is given by this and magnetic field is given by this, then pointing vector can be calculated as 1 by mu naught E cross B. And when we put the value of E and B, this term will become cosine square. And then we use this identity of cosine square that 1 minus 2 cosine square theta is equals to cosine of 2 theta. And when we use that, this is the expression we are left with pointing vector. So we have to calculate the average value of this pointing vector to calculate the intensity. So whenever we wanted to calculate the average value of any function, so we will consider a time interval t within which we wanted to calculate the average value, and it is given by the length of this time interval into integral of this function over that time interval. So the pointing vector s average value within the time interval is given by 1 by t 0 to capital T s t dash. So we have to integrate this expression. This is the that one. All of these quantity are constant. The t dependence is inside this cosine argument. Since we have mostly going to integrate the t dependence, for the sake of simplicity, we can put z equals to 0 here. If you do not want to put it z equals to 0, you can keep it, then just solve the equation again. I have just simplified it by putting z equals to 0. So these terms are constant. They are come out of integral. This is 1. It will give this extra expression, and this cosine integral, which when we put z equals to 0, is left with this cos 2 omega t dash. So when we integrate it, it will become minus sine 2 omega t, and then we put capital T in place of t dash. So capital T, we are left with 2 omega capital T, and omega is 2 pi by t, unless we have been said that we have to change our omega, we are not going to change it. So this is the default value of the omega, which is 2 pi by capital T. So when we put the value of omega and t dash here, this term will become 2 pi, actually 4 pi. So sine 4 pi will also become 0, and sine 0 is also become 0. So basically in both the integral limit, this term is going to be 0. Only this term is going to be survived. And this t will then cancel out with this t. So the average value of Poynting vector is given by E naught P naught by 2 mu naught. And for EM wave, P naught is E naught by C, where C is given by this expression. So when we put the value of P naught, then average value of Poynting vector is given by this. And this is what is known as the intensity of this EM wave. There are two special cases that are we are going to discuss here for the intensity. Let us consider that the electromagnetic wave is falling normally onto a surface of some material which can completely absorb it. And this case is generally applied for the case of black body, which can absorb all the radiation that is incident on it. And we have to calculate what is the pressure that is going to face by this surface. See, it is very much like there is something which is coming at very high speed since it has a momentum and it hits some surface. So basically the surface is going to feel some kind of pressure. So we have to calculate what is the pressure that is felt by this surface due to the hit of this electromagnetic wave. So pressure is given by force upon area, and force is given by rate of change of momentum by in area. So this is our pressure. So we have to calculate what is the change in momentum. If our initial momentum that is carried by this EM wave is P, so that and the final momentum since the wave is completely absorbed by the surface is 0, then the change in momentum is P initial minus P final. So the change in momentum is P. So the momentum density, which is given by S vector by C square, the average value of this momentum density is average value of S by C square, which is equals to 1 by 2C epsilon naught E naught square. So the momentum is equals to average density, momentum density multiplied by volume. So volume we are going to consider here again is smallest tiny volume for this surface. So the radiation pressure is given by force upon area, and so which is rate of change of momentum divided by area. So the rate of change of momentum, this term dp by dt is given by g into ac into delta t, and this term delta t into area. So the pressure is given by g into c, and g is given by s by c square. So epsilon naught e naught square by 2c, and one c is cancelled out. So this is the pressure term, which is 1 by 2 epsilon naught e naught square. And since the intensity that we have calculated is 1 by 2 C epsilon naught E naught square, so this pressure term will become I by C. So for the case when the light hit directly a surface and it is completely absorbed by that, then the pressure felt by that surface is given by I by C. Similarly, for the case of perfect reflection, If there is a, let's say, mirror which can reflect the complete light incident on it, so the initial momentum of this wave is initially, let's say it is P. So after reflection, the momentum is again going to be P, but since the direction get opposite, so there is a negative sign. So the change in momentum, which is P initial minus P final, is 2 times of P. So hold the pressure P, which is depend on the directly proportional to this rate of change of momentum del P by del T into A. Our momentum get double, so our pressure will get double. So here the pressure will become 2I by C. This is for the case perfect reflection, and this is for the case perfect absorption. There might be some cases whenever there's certain percent of reflection and certain percent of absorption. We will see it next. So this is the basic thing regarding this pointing vector. So with that, we are going to solve some questions from GATE exam. So this type of question is coming in GATE 2018. This is the question number 22, in which is question given. A light beam of intensity I naught is falling normally on a surface, and the surface absorbs 20% of intensity and rest of it is reflected. We have to find the radiation pressure on the surface in terms of I naught by C. So there might be some factor here that should be coming. So we have to find what that factor is. So if your incident light is carrying an intensity I naught, so 20% of this light is absorbed. So 0.2 times of I naught get absorbed, and the remaining 0.8 times of I naught kinds of reflected back. So if our initial pressure here is given by P, then the pressure which is reflected back is given by 0.8 times of P. But since direction is opposite due to reflection, so there is a negative sign. So this is given by P initial and P final is minus 0.8 P. So the change in momentum is P initial minus P final. So the P initial is P and we put the value of P final. So the change in momentum is 1.8. Since the radiation pressure directly proportional to this change, so our radiation pressure will become 1.8 times of this I by C. The similar way we have calculated for reflected case. So the multiplication factor that is coming here is 1.8. So this is the answer here, 1.8. So whenever you encounter this kind of question in which certain percent of light is absorbed and certain is reflected, just try to see how much the intensity, how much the momentum is changing. Based on this factor, you can calculate what is the radiation pressure will be. So, okay. So the next question is also from GATE 2018 exam. So the question number 32. A long straight wire having a radius A and resistance per unit length R carries a current I. The magnitude and direction of pointing vector on the surface of the wire is. So we had given that a wire is carrying a current A. So we have to find what at the surface of this wire, what is the magnitude and direction of this pointing vector. So pointing vector is given by E cross B. So we have to know what is our electric field and what is our magnetic field. So the magnetic field due to a straight wire is given by mu naught I upon 2 pi r. The direction is phi cap. If this is the direction z cap, you can hold your, you know, you can hold your wire in your right hand. Then your finger will give the direction of magnetic field. So this is the analogy used to calculate the direction of magnetic field. So magnetic field, we know at the surface radius r will become a. So this is the magnetic field. Now we have to know what is the electric field due to this straight wire. See if the current is flowing in this direction. So this is the negative direction, this is the positive direction. So there is an electric field, this is set up here. Or the another way to calculate the electric field direction is from Faraday's law, which says that whenever There is an electric field that is induced due to the change in magnetic field, and the direction of this electric field is the same as direction of current. So basically, your electric field is going to be in z cap direction, and the magnitude of it is given by gradient of potential minus del V by del R. So basically, it is potential by some length element. Let us not consider here dr, just length element. So the potential is given by, let's say, V upon L, and potential we know that is given by I into R. I is the current, R is the resistance, L is the length. And it is given in the question that resistance per unit length is a small r. So resistance per unit length is a small r. So whenever we take potential V upon L, so this quantity will become uh, V, we will put IR upon L. So R upon L will become small r. So this is the electric field due to this wire, IR in the Z cap direction. So we have to calculate the Poynting vector S, E, which is mod E cross B. So
Ma'am, what
here,
will be the direct dimension of small r here?
this is the resistance upon length, na? So ohm resistance, ohm by length meter.
Okay.
Uh, the resistance, the dimension of resistance is ohm, na?
Yeah.
This is ohm by meter. This is the dimension of small r here. So it is given in this question that resistance per unit length is R.
Okay.
So we are calculating Poynting vector S. So here I have turned it into magnitude. Otherwise, you can calculate E cross B too. So the E is given by IR, B is given by mu naught I upon 2 pi A, 1 by mu naught. So basically, the direction is Z cap multiplied by phi cap. So if you are looking for a cylindrical coordinate system, Z cap cross phi cap will give you minus R cap. So if this is your Z cap direction and this is your XY coordinate system, such that this is the phi cap, this is your R cap direction away from the origin. Minus R cap means towards opposite side. So here minus R cap, they are saying that it is inside the plane if positive R cap is outside the plane. So this will become I square R upon 2 pi A. So I square R upon 2 pi A perpendicular to the axis of y, which is z cap. Obviously, r cap is going to be perpendicular to z cap, and it is pointing inward. So this is the answer here. There are other questions too, which are solve similar formulation, in which electric field is calculated by this type of formulation. You can find in this NPTEL lecture of this IIT Kanpur NPTEL lecture. So this is the easiest analogy to calculate the electric field. Okay, so is it clear this question?
Yes, ma'am.
Okay. So next question is also from GATE 2018. This is question number 48. An electromagnetic plane wave is propagating with intensity 1 into 10 raised to power 5 watt per meter square in a medium with epsilon 3 epsilon naught, mu equals to mu naught. What is the magnitude of electric field inside the medium? So we are given the intensity I inside the medium. So we already know that the intensity is given by 1 by 2 C epsilon naught E square in free space. So inside medium, epsilon naught changes to epsilon, mu naught changes to mu, and the speed of light in free space changes to velocity of light inside medium. So velocity is given by, like C is given by 1 by square root of epsilon naught mu naught. Velocity is given by epsilon into mu, and epsilon given as 3 epsilon naught, mu given as mu naught. So basically it will become C by root 3. So this is my velocity of this electromagnetic wave inside medium. So inside the expression of intensity I, which is given by 1 by 2 epsilon V E square. We have to calculate E, which is square root of 2I by epsilon V. So I is given by 1 into 10 raised to power 5. We have multiplied by 2. Epsilon is 3 times of epsilon naught multiplied by V, with V is equals to C into root 3. Then we put this value. The value of electric field is given by 66 into 10 raised to power 2, and which can all be written as 6.6 10 raised to power 3. Since 10 raised to power 3 is already written, so 6.6 is the answer for this question. So mostly formula based kind of question you are going to encounter with a very little conceptual change. So this is the question number 4 in GATE 2017 exam. A monochromatic plane wave in free space with electric field amplitude 1 watt per meter is normally incident on a fully reflecting mirror. The pressure exerted on the mirror is, in this case, electric field is given, which is 1 watt per meter, and we have to find the pressure. And it is a fully reflecting case. So fully reflecting case pressure is given by 2I by C. I is given by 1 by 2 C epsilon naught E square. So pressure can be calculated as epsilon naught E square. 2 and C will cancel out. So this is the value for the pressure since 10 raised to power minus 12 is already given. So 8.854 is the answer for this question. Now this is the question number 40 in GATE 2016 exam. The electric field component of a plane electromagnetic wave traveling in a vacuum is given by E naught cos kz minus omega t I cap. The Poynting vector for the wave is. Now we have given electric field vector. We have to calculate the Poynting vector, and for that we must know what is our magnetic field. Since Poynting vector is given by 1 by mu naught E vector cross B vector. So we are going to use this formula for the calculation of magnetic field. And this is valid for EM wave in free space. So in free space, magnetic field B is related to electric field by this formula 1 by C K cap cross E vector. We will drive this formula later. There is one more question that is encountered in which we will calculate this, how this came. So magnetic field is given by, here the K cap direction is given by what is this argument is. So whenever you wanted to take the gradient of this kz divided by magnitude of this kz, k will cancel out, so the direction will become z cap direction. So the k cap direction is the z cap direction, and the direction of E vector is given to us as the S cap direction. I have taken this I cap by X cap and J cap by Y cap and K cap by Z cap. So just don't be confused here. So magnetic field is given by exactly same expression E naught by C cos kz, Z cap is the K cap direction and cross X cap. So this is my magnetic field. So the Poynting vector is E cross B. So it will become E naught square mu naught into C cos square kz. So this Poynting vector is in the form of E naught square by mu naught, but the answer is given in terms of epsilon naught. So we will use this formula C square equals to mu naught epsilon naught, and mu naught C is replaced by 1 by epsilon naught C. This will give the Poynting vector epsilon naught C into E naught square. So this is the correct answer here. The Poynting vector is in the z cap direction. You're already familiar with that. The Poynting vector direction is always going to be the k cap direction, even if you do not calculate this E cross B. Okay, so this is again a formula-based question in 2014 exam. The intensity of laser is given, and we have to find what is the magnitude of electric field. So intensity is given, magnitude of electric field can be calculated using this formula. This is the same question that we have encountered previously. This question is little different. This is coming in GATE 2012, and there is a concept that is involved here. In this question, it is given that the space-time dependence of electric field of a linearly polarized light in free space is given by this. So basically, we know what is our electric field is, and we have to find what is the time average energy density associated with electric field. So we have not asked for the EM wave, we have asked for the electric field and also for the time average value of energy density. So energy density, which is given by 1 by 2 epsilon naught E square for the electric field, average value of it is given by average value of E square. So we have again encountered with this average value of cosine square. So whenever we try to calculate the average value of cosine square or sine square with respect to t, it is always going to be half. So you can try by yourself. This quantity will give you answer which is p by 2. Not this one. This will give you t from there. So 1 by 2 is coming from this form identity of cosine square. So your answer for the average value of intensity, average value of energy density for the electric field is 1 by 4 epsilon naught E naught square. So you have to be careful whenever you read the question. Are they asked for the EM wave or they ask for the particular electric or magnetic field? And also taken care of this average value or this simple value. Since a factor of half will came whenever we are trying to find this average value. Okay. So this is the question coming in GATE 2011. Oh, there is a small concept also involved in this question. A plane electromagnetic wave has a magnetic field which is given by this expression. So basically this time you have to calculate what is your propagation vector. It is not simple here. So you have to find what is the electric field E. So for the EM wave, as B is related to E is also related to B by this relation, which is given by minus C K cap cross B, and this relation E naught by B naught. They are all varied in free space. So we have to calculate electric field from the knowledge of magnetic field. So we can calculate K cap cross B vector, and the K cap is given by take the gradient of this vector, which is inside this with K vector with K, which is x plus y K root 2. Take the gradient of it and divide by this magnitude. So basically you are left with x cap plus y cap root 2. So this is your k cap vector. So your electric field would be minus c and this whole coming from this b terms and multiplication of this k cap cross z cap. Z cap is the direction of z b vector. So this vector is k cap cross b vector. This is coming from b vector. So this is your electric field. When you take x cross z, you are left with minus y, but since there is a negative sign, so it will become plus, and y cross z will give you positive x, but because of negative sign, there is negative. But if you look at the options, the option is your I should be positive and y should be negative. But in the calculation, y comes out to be positive and x is negative. The option is correct, but where we are doing wrong in the calculation of this propagation vector. If you look at the argument of this question, the sign of k and the sign of omega, they are both positive. And when you try to see how your wave is it propagating in positive direction or the negative direction? So let us consider that you have some simple wave, there is some function in which both positive x component and the t component both are positive. So in case of propagation, this term, this which is inside the bracket, that has to be constant. So this phase, the term which is inside this bracket represents the phase, and as the wave moves, this is the phase term that is moving. So this term has to be constant, That means d by dt of this term with, will not going to be changed. And when we try to differentiate E, it give an expression dx by dt as minus omega by beta. Omega and beta are some positive values. Let's say some constant. So dx will become some constant times dt. So if your time is increasing, that is with time, your x is decreasing. That is, your wave is propagating in negative direction. So whenever this kind of condition arises, that when your both t component and the x component, they are both positive. It means that with time, your wave is propagating in negative direction. So you have to apply negative sign by yourself in this case. So there is this negative sign that we have forgot to apply here, and that will give you here negative sign and positive sign that is available in the option. And similarly, you can ask when it will be going to in the positive direction. Well, whenever the sign of this x component k vector and this omega times term, they are in opposite. Then you calculate dx by dt, it will become positive constant value. And then if your time increases, your x is increases. That is, your wave is moving in positive x direction. So in that case, you will take your propagation vector k in positive direction. So the thumb rule is whenever the sign inside this bracket, they have both same sign, then the wave is going to move in negative direction. And when there is a positive opposite sign, it is going to move in positive direction. So the correct option here is A, and this is coming because of this. Now we have to calculate the Poynting vector. We know our magnetic field, we know our electric field, we can calculate the Poynting vector just by E cross B. And when we calculate the, oh, it is given that we have to find the average value of Poynting vector. I missed this thing, I guess, in question. Yes, we have to find the average value of Poynting vector. So average value will give cosine square term. If there is sine square or cosine square term, this will become half in average case. So this Poynting vector will become negative of this. So the option here, the correct one is with negative x. This D option is correct. Okay, similarly, there is this question that is coming in GATE 2010. So consider a propagation of electromagnetic wave in a linear homogeneous isotropic medium with permittivity epsilon and permeability mu. Now we have to find which from the Maxwell equation which are the options are correct. So we have four Maxwell equation and four options. Four terms are given and they are all coming from a Maxwell's equation. So the way to solve this question is you have to express your electric and magnetic field in terms of exponential, just to simplify things. So the first Maxwell equation is divergence of E equals to 0. So when you try to calculate divergence, del by del x of this term in the x cap, del by del y of this term in x cap, y cap. So this is the divergence. So when you try to calculate, let's say for one term, del by del x, this term will come out and only kx will survive. So ikx will come. Similarly, del by del y, iky. When you take del by del z derivative, there is an ikz. I guess you will get it what I have done here. It's just chain rule in differentiation. That is, when we try to take del by del x, so we will differentiate this term, and again we what is there inside this exponential, and del by del x of this term is 0, and del by del x of z term is 0. So only this term is going to survive. So similarly for y case, this term survive, for z case, this term. And when we take complete divergence, it will become I, kx, x cap, ky, y cap, kz, kz, and this term, which is the electric field term. So this term will become k vector dot E is equals to 0. K vector dot E is 0 in all cases. in all the options. So whenever the simplest thing is whenever there is a del, use ik, and whenever there is a temporal derivative del by del t, use minus I omega. Because if you wanted to take del by del t of e to the power ik vector dot r minus omega t, this is the term that is going to be outside. So let's say for the second Maxwell equation, we say divergence of H is zero. So with divergence, we replace with ik. So we'll say k vector dot H is zero. Third Maxwell equation says curl of E is equals to minus mu del H by del T. Del is replaced by ik, and del by del T is replaced by minus I omega. That will replace its negative sign. So curl of k vector cross E vector is equals to omega mu H vector. I will cancel. Similarly, fourth Maxwell equation will give you curl of H equals to epsilon into del E by del T, and curl is replaced by I cross. It will become minus I omega. So with k vector cross H vector is minus I omega epsilon. So we have to see these two terms are there. With k cross E, which term survive? Positive term, and with k cross H negative term. So with I think option A and D are same. This seems to be same. No, there is a difference of mu or epsilon. So in my case, k cross H will contain epsilon and k cross E will contain mu. So this is mu and this is epsilon. So D option is correct here. And now there is this question. If we change the sign of epsilon and mu, let's say make it negative, then the direction of propagation vector k and the pointing vector are related. We have talked that the S vector and k vector they are going to be in same direction. But if we change the direction of epsilon and mu, how these things are going to be affected? Are they going to be parallel or become anti-parallel? So for the EM wave, S vector is given by this, and we will know that it is related to electric field like K cross S cap. So S vector will become be replaced with magnetic field with this expression. So we are left with this vector triple product. We use this triple product rule. So k cap will become outside. This term will become scalar, and k cap E vector. So electric field always going to be perpendicular to this propagation vector. This is the transverse characteristic of this EM wave. So this term will become zero. So the pointing vector will become 1 by mu c mod E square k cap. Now if I change the sign of mu, my S vector will become negative of this k cap. So they will become anti-parallel. So if we change the sign of epsilon and mu, then k and s will become anti-parallel. So this is the correct option here. So with that, these questions finish. So if you have any doubt, you can ask. They are mostly formula-based questions with little concept. So is it clear?
Yes, ma'am.
Okay, then we will finish today's class. Okay, thank you. Bye bye.
Thank you, ma'am. Bye bye.